Hey everyone. So in the previous tutorial we built this audio rate phase locked loop using gen tilde. And the idea for this video is to extend this a little bit to look into some more musically interesting use cases of this type of algorithm. And basically here I cleaned up just a little bit the patch that we built in the previous video, and added a couple of samples here that we can use to try how this works on general audio samples rather than perfect sinusoids and square waves. So for example here there is this saxophone sample. And if we reset the PLL here, we hear that the PLL is somewhat accurately tracking the pitch of this input sample. But a couple of things that we can note is that one thing is that, of course, it's not only the pitch that is changing in this saxophone sample, but also the volume envelope of this signal. And this is one thing that we may want our algorithm to be able to do as well, to track the volume envelope of the input signal and apply the same volume envelope to our output of the PLL. And another thing that we can note that is that we have these periods where the input pitch is somewhat ambiguous and the PLL is not accurately tracking it. So we may want to have some kind of solution to this where we attenuate the output whenever the PLL is not certain, so to speak, about the pitch of the input. So we can start with trying to implement this, and one way to do this is to track the envelope of our input signal and feed this as an input to the gen algorithm and simply apply the same volume envelope in gen. So since this is, we could also do this inside here, but since this is fairly straightforward using basic Max objects, we will compute the signal using regular MSP objects. And we can, for example, use the average object, which takes a averaging interval, which we maybe can have as a parameter as well. And then we have a mode, and now let's use root mean square averaging. So if our input goes here. We can create a scope with the range 0 to 1 and see that now we have kind of envelope tracking. One thing we can also add to this is the peak amp object. Which also takes an interval. Let's maybe use 100 milliseconds. And now we will output the peak value of this signal over the past 100 milliseconds. And this works well with the peak object, which needs 0 to initialize it. And now what we get out here is the maximum of these reported values over time. So anytime a larger number comes in, we increase here the maximum. And we can send 0 whenever we want to reset the peak to 0 and recalculate it. And now we can divide our amplitude signal here with this peak value. Divide signal like this. And now we should have scaled this signal between 0 and 1, where 1 represents the maximum of this signal over time. And if we send another audio sample here, we need to reset this maximum to recalculate it. So that is one way to create a envelope follower, essentially. So this is envelope follower. And now we can add an input here in our Gen PLL implementation. Let's call it envelope, a third inlet. Then we can move our reset button and send this envelope. And now we can simply multiply here our output with the envelope. So now we should have something that also tracks the envelope of the input signal. So that works well. Then regarding the uncertainty here, one thing we can of course do is to now also divide x, our input signal here, by this envelope signal to sort of normalize the input volume to be as close to 1 as possible, which might give this PLL a bit more certainty, because we essentially apply a compression, I guess we can call it. So if you divide x by envelope, and what we can note generally, if you look at this phase error, now signals are quite small. Maybe we can scale it down to minus 0.5 to 0.5. So if you pay attention to this phase error in the IQ plot, like when we are locked into the input frequency, we generally have a larger magnitude here. So if you remember, this IQ plot is in a way like a point on a circle in the ideal case, and the larger the radius of this circle, the closer we are to a perfect locked-in PLL, essentially. So one way to measure a confidence is to compute exactly this radius. So from the previous tutorial, if you remember, this I and Q are the points in a 2D plane, and the distance of this point to 0 is the radius of that circle, and that we can compute here, of course, using the trigonometric formula. So essentially radius is square root of I squared plus Q squared. And our filtered I and Q here are the I and Q that I wrote here. So let's maybe call this confidence. We write square root of the I component to the power of 2 plus the same Q component to the power of 2. So if we output this confidence, we see some signal that is changing a bit, but is generally larger when we are certain about the frequency of the input, and lower when we are uncertain about it. But it is also changing quite rapidly, so maybe we want to add some smoothing to this. So we can use yet another one-pole low-pass filter for this. So let's call this confidence low-pass. And we can create yet another filter coefficient here. Maybe call this alpha 2. And we can set whatever low pass frequency we want here, and maybe we want something quite low here to create a smooth confidence signals. So maybe 2 Hertz could work. And then we update the confidence low pass in the same way that we did for the INQ component. So we have our alpha 2 coefficient, the previous low pass output, and then 1 minus the filter coefficient times the input, which is the confidence, the raw confidence value. So now if we output the low pass confidence, we see a bit smoother value. So then we can apply this in addition to our envelope. So the envelope controls the amplitude of the output, but we also control it with the low pass confidence value here. And now it's quite low volume, so maybe we can also introduce a gain parameter here. So we scale it with a gain and create a parameter gain 1 by default. And then we can also control this gain. So essentially this removes a little bit of these artifacts, which are kind of common sound of the PLL type of algorithm, which may be something that one wants to have or wants to remove, depending on what sound we want to create. So another thing we can try here is to do a pitch or input frequency dependent frequency shifter. And the good thing about the PLL is that we have here both the in-phase and the quadrature component of the NCO in the PLL. And this is exactly what is needed to do frequency shifting. So the way this would work is that we not only output the cosine here, which is the in phase, but we add two more outlets with the I component and the Q component of the PLL. So this is, and maybe we can skip the confidence. We don't really need it anymore. So out 5 and 6 are now our NCO in-phase and quadrature components. And maybe to keep things cleaner, let's make a send here and send our input signal, and then we can receive the input down here. And a one-sided pitch shifter can be achieved here with the Hilbert object. So the Hilbert object is applying the Hilbert filter to a input signal, and what we get out from an ideal Hilbert filter is the I component of the input. So it splits the signal into two signals, one in-phase component and one out-phase component. So you see here the cosine or the real valued input, and this is the sine or the imaginary output, so the Q component. And then for pitch shifting we multiply the in-phase with our in-phase oscillator and the quadrature component with the sine or quadrature component of the input, and then the frequency shifting works as follows: that we add these two together to create the negative sideband, as it's called. So this is pitching down, and if we subtract, we create the positive sideband, so pitching up. And this means that we now have our input signal, we track the fundamental frequency of it using the PLL, and then we apply this oscillator to frequency shift the input with its own fundamental frequency. So if we listen, for example, to the negative sideband, we get a very weird glitchy effect. And the positive sideband, we have shifted the frequency spectrum up. Maybe we can look at the spectrum from 0 to 20,000 hertz. So this is pitching down. This is pitching up. And with the synth input, yeah, we get these very weird artifacts when the PLL goes in and out of lock, which can be kind of cool. And then another idea we can try, of course, is in our output of the raw waveform from the PLL, since this is a signal output here, we can apply whatever processing we want to this. So we can, for example, do wave shaping of this cosine. And one way to do this is with the tangents function. And then we can add a multiplication here with yet another gain factor, which we can maybe call saturation, or actually it's fine to just scale the gain here. So maybe skip this. We have this amplitude dependent wave shaping of the output, which causes this to become increasingly more square wave as the amplitude increases, which gives it a little bit more responsive feel to it, almost like we open up a low pass filter as the amplitude increases. And we are not limited here to just output the fundamental. So, for example, we can create yet another outlet here and copy this wave-shaped cosine. And if we multiply the phase by 2, for instance, and listen to this output, we should get the octave, 1 octave above. So now we can mix between the fundamental and the octave. And if we want a perfect fifth, for example, we can multiply with 1.5 here. So I added here a reverb and tuned the parameters a little bit, which creates a little bit of a interesting ambient structure. Although quite chaotic at times. Right. So that is, I think, it for this tutorial, and it should give you some ideas, hopefully, how this can be applied in a more musical context.